Welcome back to The Explainer. Today, we're skipping the basic stargazing and diving right into something truly wild. We are going to look at a stellar phenomenon not just as a beautiful picture in the sky, but as a literal functioning cosmic engine. We're going to break down the sheer mechanics of the star cluster Caldwell 50 and see exactly how it drives one of the most famous formations in our entire galaxy.
Right here is the glowing heart of Caldwell 49, widely known as the Rosette Nebula. But notice that vast, dark, circular cavity right in the middle? It looks almost like a hollowed-out shell, right? Well, that dark central space is the exact location where our engine lives. That is the open cluster NGC 2244, better known to most of us as Caldwell 50.
To really give you a sense of scale here, this massive cosmic machine is located exactly 4,700 light-years away from Earth. It sits way out in the Monoceros constellation, bridging this immense, incredibly quiet gap of space between us and what is honestly an incredibly active, turbulent stellar factory. Now, obviously, every engine needs fuel, and it needs pistons to drive the actual mechanics. Well, in Caldwell 50, those pistons are a super rare, heavy-hitting collection of massive O-type stars. These are the absolute behemoths of the stellar world, and they are the powerhouse driving literally everything we see happening in the surrounding nebula. Okay, let's dive into this. At the very core of this cluster are absolute giants. We're talking about stars like HD 4623 and HD 4650. These are essentially massive cylinders that are over 50 times the mass of our own sun. And because they're so huge, they burn unbelievably hot and bright. These O stars power the entire region just by blasting out intense ionizing radiation and unleashing these incredibly powerful stellar winds.
So all of that mechanical output and radiation from these giant stars acts exactly like a highly energetic exhaust. It doesn't just sit there in space, it violently pushes outward, slamming right into the surrounding cloud of gas and dust. It's actually this exact outward pressure that is physically sculpting the Rosette Nebula, blowing away all the lighter material to hollow out that massive cavity we saw right at the beginning.
And because of this intense radiation constantly pushing out from the center, we end up with this really stark physical contrast in the region. Right near the engine's interface, the gas gets swept out and sits at a relatively warm 30 Kelvin. But if you move further away into the remote molecular clouds, the temperature completely plunges to a freezing 10 to 15 Kelvin, while the density of the gas shoots way up. And this brilliantly illustrates exactly what we're talking about. The blue and green areas you're seeing trace those warmer, swept-out regions near the cluster, while those stark red and orange zones reveal that steep drop into the cold, dense molecular ridges found much deeper out in the cloud. It is literally a perfect thermal fingerprint of our engine hard at work. But here's the thing. This engine doesn't just push gas around, it actually builds new things. The mechanical impact compresses the surrounding gas, which triggers the birth of entirely new generations of stars. The evidence is everywhere. We see the expanding cavities cleared by radiation, we see these dense elephant trunk pillars that literally point right back toward the massive O stars, and we find clear age sequences where the stars located further from the cluster's center are actually younger than the ones inside. Let's transition for a second, though, from the violent, massive O stars shaping the nebula to the incredibly delicate, tiny byproducts being manufactured by this cosmic engine. Because right alongside the massive stars, this region is breeding something completely different: brown dwarfs. To really grasp how we know this is happening, we need to quickly define a crucial tool used by astronomers called the initial mass function, or IMF. Just think of the IMF as an empirical distribution, kind of like a cosmic recipe that describes the ratio of how many stars of different sizes are born together in a single star-forming region. It's the go-to metric we use to measure the production efficiency of full-size stars versus tiny brown dwarfs. When we look at the recipe for Caldwell 50, the shape of this curve, its specific power law slope, tells researchers something pretty amazing. It reveals a remarkably rich population of tiny, substellar objects forming right in the wake of those giant stars. Now, what's really interesting about what we're seeing here is the peculiarity of these byproducts. I mean, their masses are incredibly low, ranging from just 0.03 to 0.4 times the mass of our sun. Furthermore, they are produced with crazy high efficiency, boasting a star-to-brown dwarf ratio of about 2.2 to 2.8. But honestly, the most fascinating part These delicate brown dwarfs are found physically closer to the massive OB stars. It suggests that the extreme radiation from the massive O stars might actually be altering the local environment, stunting the growth of nearby protostars, and efficiently producing these tiny brown dwarfs right next to them. So, to recap, we have an engine that has been burning fuel, hollowing out a nebula, and triggering the birth of both massive stars and tiny brown dwarfs for about 2 million years now. But we really have to shift our focus to the future of the Caldwell 50 cluster. What is its ultimate dramatic fate?
So the crucial point is, when we track the internal movement and physical expansion of the stars inside NGC 2244, we see a very distinct pattern. The cluster's internal velocity dispersion, which is basically how fast these stars are moving away from each other, is incredibly high. In fact, it's significantly higher than what their own collective gravity can actually hold together. And that brings us to a final, pretty profound realization. What happens when a cluster is supervirial, meaning its internal kinetic energy exceeds its gravitational binding energy and it's constantly expanding? Well, it means the engine is tearing itself apart. Eventually, the stars of Caldwell 50 are going to completely overcome their shared gravity, leading to the inevitable, beautiful dissolution of this cluster as its stars scatter out into the wider Milky Way. It's an absolutely incredible life cycle to witness. Thank you so much for joining me today to explore the mechanics of this cosmic engine.